Yeah, so it is my pleasure to introduce our next two speakers. The first of which will be Stefano Sarao Manelli, who is an assistant professor of data science and AI at Chalmers University in Sweden. And he will talk about bias in motion, theoretical insights into the dynamics of bias in SGD training. Yes, we can see your slides.
Yeah.
So if you want, you
And
can
you
just
can hear me too, right?
Yes, sounds good.
Perfect. Okay, hi everyone. Thank you for having me here. I'm going to talk about bias in motion, which will be a bit of a more theoretical angle on the problem. So I'm very interested in understanding your opinion, your questions about this topic as well. Um, so this is a NeurIPS publication. It will be presented next week at NeurIPS, and it's a work in collaboration with Anchit Jain, Rosina Bahari, and Ariste Baratin. And the starting point is that I think, and other people in the community think the same, that associating bias only to historical bias or bias is present in a data set is limited. Of course, historical bias and dataset bias have a strong impact of classification performance and fairness issues among different groups in the population. But this is only part of a picture that is way more complex. So in a machine learning pipeline, you can see biases emerging and being augmented in at different stages. And I think so far there has been very limited theoretical work in trying to understand what is the role of each of these choices. Many of the machine learning design choices came from historical um, composition of findings, and sometimes we don't really know what are the effects. We just keep doing them because everybody did them before. And so just to contextualize a bit, this figure that you can see above is adapted from this paper by Suraj and Guttag, where they were proposing a framework to rethink bias in machine learning pipelines. And in the recent years, we have seen different papers pointing out roles in bias augmentation, like the architectural complexity over parameterization, pruning, even the randomness within the batches in a SGD training can affect bias throughout learning. And so this is more or less where my line of research fits. I want to understand each individual element of this complex picture and try to single out them and see how they contribute. Yeah, on this side, I'm very happy to connect with the medical image community because you have lots of fairness problems. And so I think there are lots of things that we can learn from what you do. So I will specifically talk about bias in throughout learning. So a very common assumption that we do, even when designing mitigation strategies, is that bias will remain consistent throughout learning. So in this case, you have this paper from Yu et al. In 2021 on some imbalance data problem, where you have a majority of +1 and a minority of 0 classes. You can see the performance condition to one of the two groups that is much faster, while the other takes longer time to grow. So some mitigation strategies propose to just take one instance during training, try to estimate what is the amount of bias at that stage, and then restart training and use this information to mitigate bias. In this work, we wanted to see if this assumption is correct. And so we considered this an experiment that is reframed from Bell Segun 2022, where we took the CIFAR 10 dataset. We constructed two groups, taking 4 classes in one and 4 classes in the other. And within each group, we created a label +1 and a label -1. So we created a classification task within each group. And then we combined the two groups together with a certain percentage. And these groups are not chosen at random. They come, like there is an idea behind the construction, but will come later in the next slides. And this is what you see. So you can see that you can see the performance condition to the two subgroups. And you can see that at the beginning of training, you are performing very well on the red subpopulation, but later on, you will deteriorate the performance. Instead, the blue one will catch up and outperform the red. And I think the interesting bit is that if you apply any of the strategies about rescaling the importance of the loss according to the subpopulation, given an instance in time, you may actually overestimate the blue subpopulation, giving it more importance and create even more disparity at the end of the train. So I think we should really think about these choices. And in order to understand why exactly this phenomenon is happening, we started with a modeling approach. So we created a synthetic model where we can control all the variables that is quite simple to understand and also to analyze. And it is composed of two populations given by these red and blue dots. And each population has the decision boundary. So a classifier may have to trade off in some cases because you have some inconsistency. For instance, you can see that in the blue region, the red decision boundary will predict a -1 class, while the blue decision boundary will predict a +1 class. So in particular, we train the simplest classifier we can think of. So it's a linear classifier. And the interesting bit about it is that we can characterize exactly the sufficient statistics of the problem. So by sufficient statistics, I mean some variable that can be used to identify the loss, the accuracy, or some fairness metrics like equality of opportunity that we heard of in the first talk. And this is the way the dynamics look like. Of course, in this short presentation, I cannot give you all the tools to read this equation, but what you have to see from this is just that you have some sufficient statistics that evolve as a combination of exponentials. So if you, for instance, look at the first two, you can see that there are some exponential terms that are going up going down at the beginning, and some exponential terms that instead saturates later on in training. And by looking at the exponent of this exponential, we can characterize what are the typical timescales that affect our training. So this gives us these three terms. And in the next three slides, I will try to single out their effect during the training dynamics. So we'll start with tau R and tau M. And they are very much connected with the spurious correlations. Well, spurious correlation, I think, is something that we are all familiar with, especially since we have some example of spurious correlation from the previous talk, where these elements in the corner of the image were spuriously correlated with what you wanted to predict, and the classifier was relying on those. A classical data set for this is the water birds one, where you have water birds and land birds, and classifiers tend to use the background as an information for predicting the kind of bird that you have. And so when you observe a duck out of the water, the classifier is very confused because it considers that as a land bird. So within our model, we can produce something similar. What we need to do is just creating a strong correlation between the membership in one group with the label that you want to predict. For instance, here you can see that even if I predict only the label, the group membership, I will perform quite well. I will just create some mistakes in this corner that you can see here. If I train my classifier, what I see is a loss that looks like this. So you can see there is this initial plateau, and this is exactly what emerged from the spurious correlation. So now the green line is measuring how much I'm relying on the group membership in my classification. And you can see that in this phase, when we're at this plateau, basically the classifier is using only the membership attribute to predict the label. Instead, if I wait long enough, the alignment with the decision boundary will increase, but that of course requires more computational power and more data in this data set. So spurious features are faster to learn, but asymptotically disappear, and our model is able to capture this phenomenon. So now let's consider two other time scales, tau r and tau q. For this, what I need to do is getting rid of the shift between the two groups. Now I have this hopeless task where I have two decision boundaries completely that are quite misaligned, and the clusters that are one on top of the other. And the classifier has to trade off. And when you train it, you start to observe something that is more that is similar to what we observed in the first experiment that we done. So we can see that one population is advantaged at the beginning and later on is disadvantaged. And so there is the emergence of this bias crossing phenomenon. So now if I put everything together, I can get something quite funny happening, where if I play enough with the construction of the model, I can get the classifier to favor one class at the beginning of training, disfavoring it in the intermediate phase, and finally favoring it again at the end. And the interesting bit is that using our theory, we can understand what is going on during these three phases. In particular, the initial phase, the classifier is driven by, is following the spurious correlation. And so it's attracted by, in this case, the positive trust cluster because it has a greater relative representation and a strong class imbalance. In the intermediate phase, instead, is the saliency of the stimuli that matter. And so in this case, the negative cluster is more salient. And so the classifier is attracted by that. And finally, in the last phase, the relative representation kicks back into play. And we see again that the majority group is the one that is advantaged. And there is a precise equation for this. But the general picture, I think, is more interesting because we can generalize it beyond the simplicity of this model. So for instance, we can revisit the experiment that I gave you at the beginning, where I mixed the two subgroups. And this is what you observed before. But now if I change the fraction of mixing, I can you can see that the two lines get closer and then the crossing disappears. And another interesting bit about this plot is that this is exactly consistent with the theory, because what our theory says is that only in the last phase of training, the relative representation enters into play. And you can see that basically nothing else is changing in this plot. And finally, just to go beyond, again, the simplicity of the model, this is just a series of runs that we have done on the cell-based dataset, where on the first element is the group that we are considering, and the second element is instead the attribute that we are classifying for. And you can see that even in these cases, we can have a bias crossing situation. So I'm not saying that this is something that always happens, but I think that in general, we should question some of the assumptions that we make when we design the mitigation strategies, because in some cases, it may not be true. And so now I can conclude my presentation. So what I told you is that many aspects of machine learning are given for granted. And in particular, bias evolution is non-monotonic, at least in general. And using this theoretical analysis, we can understand the role of the different statistical properties in the phases of the learning dynamics. And of course, there is a lot of work to be done next. It will be very nice to connect this with some possible mitigation strategy, but this is not. This is still a work in progress. Yeah, thank you.
Thank you so much. Super interesting. I have many questions, but of course I will give precedence to the participants' questions. While they are coming in, I will take the opportunity to start with one. So you said at one point that the spurious feature was dominating during the dynamics at one point, and then it kind of disappeared in the end.
Yes.
Empirically, we see that there are also cases where the spurious feature is still used a lot in the final trained model.
Yes.
So it doesn't disappear. Would you say that it's just because one was not training long enough, or are there also theoretical cases where it prevails in the end?
Yeah, so there are two important things here. One possibility is definitely the one that you're mentioning. So we are not training long enough. Uh, the other one is that here we are in online learning setting. So we are not revisiting samples. And I think this is a key difference that we are currently working on the offline dynamics, but it's definitely more complicated because you have correlation coming into play. But there you have another problem, which is memorization. And here you cannot really memorize sample. So my intuition, but I must wait for for the analysis to be completed, is that what you're doing is that you are memorizing some of the samples, and once they're memorized, it's very hard to get out of this local minimum, and so you are just stuck there. You will not you will never forget completely this spurious correlation.
I see. Interesting. Yeah, that makes sense. Okay, I see there's a question in the chat. One second. Like I said, yes. Oh, it's a question by Ben. Okay, so Ben wanted to ask whether the framework can be applied when different samples within the same class have different training dynamics. So in the fairness setting, it's not necessarily about one class training better than another, disease versus non-disease or something like that, but different samples within the classes might be disadvantaged.
Yes, um, that's interesting. Yes, in principle, it is possible. Uh, the main limitation is that we cannot, at the moment, I don't see a way to include some individual role. So you may consider that you have within a class some variability, and so you have a consistent but small fraction of your group or your class that has some different statistics. Yes, this is something that we can model. What we cannot model is having a single outlier, because this is a kind of mean field analysis, so that that will just disappear in the mean field approach. So what would be the question in that case? Because I'm interested in like possible follow-ups. This is something that's interesting. So if there are some possibility, I'm curious.
He would probably be interested in that. Yeah. So maybe I will ask one last, hopefully quick question. So you teased that you will be interested in mitigation next. So I mean, this your talk raises the obvious question of how to exploit this new knowledge for designing better mitigation strategies. Can you maybe give a hint at something that you're interested in looking at?
Yeah. So one thing that we start to look at is decoupling. And this is again a limited method, but we are assuming that you know what are the groups, which in some cases you do. You can design two different classifiers that are trained in parallel while being connected throughout the learning dynamics. So you want them to be independent enough so that they are able to classify the different subpopulation, like, well, for instance, in this example. But at the same time, there is some shared knowledge. And so adding some coupling within these two classifiers should improve the situation. And this is something that we can still analyze within the framework. So that's a first starting point.
All right, very cool. Thank you so much.